So with the Ohm's law and the power equations, it gets kind of exciting because there's the potential for lots of real-world applications. For example, the other year we had a family reunion in town, and one of my uncles or cousins wanted to come with their RV and park at our house and plug in their RV. So I needed to do some calculations as to what might happen in a very long extension cord that would go from the house to where their RV would be. So I estimated it was about 200 feet. And I guess I figured we'd get the slightly not cheap 14 gauge cord. They have a 16 gauge, which is even thinner than 14 gauge, but I assume 14 gauge for this application. And on the internet you can find the dimensions for all gauges of wire. I found the diameter, but the radius is half of that, and the area is pi times the radius squared. And we're finding the cross-sectional area because that is going to be included in the equation that relates resistivity to resistance. I'm curious to find the resistance of a 14 gauge cord. Once we know the resistance of the cord, we can do a lot of things. It'll help us calculate power, current, etc. Now the resistance of an object is its resistivity, or hopefully like a cylindrical object like a wire. Resistivity times its length. The longer the electrons have to go through, the more distance, the harder it is to do that, the more resistance they're going to encounter, divided by the cross-sectional area. So the bigger, the wider the highway, the more lanes on the highway, the smaller the resistance is going to be. And you can Google the resistivity of any material. There's a table in your slides. It has the value for copper in there. If you get an extension cord, there's almost 100% chance it's going to be a copper cord. Now here's where it might get a little too complicated. I'm going to use 200 feet as a length. But this might be equivalent to just a 100-foot cord that you buy at the store. Because for one extension cord, you need two different wires. You need one wire, the hot wire, to bring the voltage out, and then you need a neutral wire for that current to come back. The circuit goes back and forth all the way around. So this 200 feet, if we use that number here, we might just be describing the resistance in a 100-foot cord that you buy at the store. When in doubt, use SI units, and this is pretty complicated here, so we definitely want to use SI units. Convert to meters. There's about 3 feet in a meter. Might have approximated a little there, but this is going to be pretty darn close at least. And divide by the cross-sectional area we just found, and that should be the resistance of the wire, about a half an ohm. Alright, so now let's first calculate the voltage drop over the cord. For this we can use Ohm's law, and that's the voltage drop, but we need to figure out the current first, and for that we can use that 200 watts of power. So knowing that power is current times voltage, and this is definitely a household 120 volt circuit, and we're using 200 watts of power. That leaves us with the current as the only unknown. So that current in that wire should be 1.66 amps if it's using 200 watts of power. So I'm going to plug in our current and resistance and find a 0.9 volt drop. So whatever you plug in is getting 0.9 volts less than it would if this was a very short cord. Now let's look at when you're using an 800 watt. You're definitely going to be pulling more. So plugging in 800 watts over 120 volts, we get 6 2/3 amps. And we plug that in for the current and get a more significant voltage drop of 3.6. And we can kind of see that the voltage drop is going to be linearly dependent on the on the current. So they are directly proportional voltage. So if we nearly double the if we nearly double the power and the current, we're going to nearly double the voltage drop. There we've nearly doubled the power to 1500, which means we'd be pulling 12.5 amps in that circuit. And now we're getting close to what a normal 15 amp circuit can handle. If we were to get just a little more, up to 15 amps, that might trip our breaker. And now we see that doubling the power, or nearly doubling the power, nearly doubles the voltage drop. So you're getting up to a kind of significant voltage drop. You got, almost 7 volts less that you're giving whatever you plug in. I know somebody who had a power fluctuation, and a different, their household wasn't suddenly getting 120 volts, and it broke half their appliances and their speakers and such. So if you're plugging in a fan or something, you might see it run like a little bit slower. But yeah, don't take some nice electrical equipment that you like a stereo or an appliance, and plug it in Europe where there's 100, or not 120 but 240 volts in the outlets, because it might just break your electronic device. Okay, now let's look at the power loss in the wire. So how much heat per time are we losing? How much of the electrical power is actually turning into thermal energy? And IV is the equation you guys should know by heart. But also it's handy to know that I squared R is that's from the handout. That's a handy equation for line loss. And it's handy to use that one because we don't necessarily know what voltage is dropping in the wire. We definitely don't use 120 here. It's just the voltage that is being lost in the wire. But we actually do know that in this situation because we just calculated it. A 1.5 watt loss is not much. And just to mix things up a little bit, let's derive that equation for line loss. The voltage drop varies according to current, and using Ohm's law, we know that voltage drop is current times resistance, and that's what we get when we insert that. And this is the equation I squared R from the line loss handout. Now 24 watts, that's more significant. And let's go back to IV just for the fun of it. We decided the voltage drop for 1500 watts was 6.75. Now that line loss is equivalent to a pretty powerful light bulb. That's just wasted electric energy as heat. Now my uncle probably would have needed a 30 amp circuit. That's usually what you got if you're plugging in some kind of RV or motorhome thing or camper trailer deal. So let's say he was pulling 20 amps out of the 30 amps max in that circuit. Using I squared R again, plug in 20, square it, times our resistance of that same cord. And that's a little bit more power than my small space heater puts out. So true story. In the last week, I've plugged in an inflatable hot tub, and I used at first I used an actual 100-foot 14 gauge extension cord, and it was outside, so I put a bucket over the cord that was all wrapped up. And after a few hours, I went to look at the cord, and it was actually hot. I could actually feel how warm the cord had gotten. I actually talked to an electrician about putting in a 30 amp outlet for an RV to plug into, and they said they would want to run a 6 gauge cord out there, which is huge. Mostly 12 gauge is pretty good for a house. 10 gauge is like like for big appliances or whatever, if you have an instant water heater, uh, that pulls a ton of power, and they use 8 gauge wire, but you know they want to use 6 to run the cord out with. But I did a little bit of calculation. I figure I could have gotten away with 8 gauge maybe.